Okay, sir, here's the second video. This video is to show and prove why why my equations or the things I thought of are right. So pretty much how I came to, thinking of these equations right here is pretty much an extension of the equations that we were taught in a previous lesson. It's just partial p partial y is equal to partial q partial x. And if this equation was satisfied for a vector field equation, that means that vector field was a conservative field. But the reason this doesn't work for like a 3x1 matrix is because it only has two things in it. So I just extended it to 3 dimensions, and I'll just show you how that works. So pretty much, here's my equations first, and how I got to these equations is this. So say del f, as we know, is just partial f with respect to x and partial f with respect to y, partial f with respect to z. This first part equals p actually. This equals q, and this equals r. If we actually plug these values back into these equations, we'll see why these equations are true. Because if you just, if you factor this p out and bring it to the side, keep this thing the same, and in fact substitute p, this stuff, and for p we get this. If you do the similar thing, bring this q out to the side, and then substitute this in for q, we get that, and same thing for this. And now, if we just multiply all these three things together, we're going to get partial cubed f, partial y, partial z, partial x. Oh man. And then you're going to get partial cubed f, partial x, partial z, partial y, and then partial cubed f, partial x, partial y, partial z. And as you know, if you just take a quick glance, these are the exact same thing. It's just that the partials are in different orders. As we know by Clairaut's theorem, I don't know how to pronounce that, these are essentially the same. That's why these equations work.